Today's speaker is Gergő Nemes. He is from the Alfred Rényi Institute of Mathematics in Budapest. And he did his PhD actually at the Central University in Budapest. And what's maybe even more remarkable, he already started publishing in asymptotics and special functions as an undergraduate student. And maybe even more remarkable, none of his supervisors for his PhD knew anything about asymptotics. So it's all his own work that he did. When I myself started my PhD more than 25 years ago, the two gods in integral asymptotics, they were Roderick Wong and Nico Temme. And whenever they gave a big overview talk, they always mentioned that in integral asymptotics, the main problem that they still had was there were no rigorous, sharp error bounds for integrals. And they were competing with the work by Frank Oliver for differential equations. For differential equations, there were extremely sharp error bounds, all based on the machinery by Frank Oliver. And there was nothing similar for integrals. And but in the meantime, they do exist because, so Gergő, his work is based on work by originally Dingle, Michael Berry, Chris House, and especially Bill Boyd. But he takes all that machinery and he will show in this talk extremely sharp error bounds, in many cases even better than what Frank Oliver produced via differential equations. And this is about for many special functions. So please go ahead, Gergő.
Okay, thank you very much, Audrey, for the introduction. And let me thank the organizers for providing me the opportunity to give a talk in this program. So in the theory of asymptotic expansions, roughly speaking, there are two main sets of methods for obtaining error bounds. One set starts with an integral representation. The other set starts with a differential equation or a difference equation. And as Audrey mentioned, when we are talking about differential equation methods, we must mention the work of Frank Oliver. So Oliver developed a quite general and rigorous theory for asymptotic expansions of solutions of certain differential equations. And he summarized his theory, or part of his theory, in his famous 1974 book, Asymptotics and Special Functions. And the main advantage of his methods is that they, as already mentioned, produce sharp error bounds and also recurrence relations for the coefficients in the asymptotic expansions. Now, around the same time, there was another theory developed by theoretical physicist Robert Dingle, whose name has been mentioned already several times during this program. So Dingle had a quite different vision on asymptotic expansions than Oliver. Dingle's intuition was that asymptotic expansions are coded representations of functions, and the main task of asymptotics should be to decode these representations. And Dingle himself also wrote a book, here it is, Asymptotic Expansions, Their Derivation and Interpretation, where he summarized his theory, which he called interpretive theory of asymptotic expansions. So Dingle, instead of bounding remainder terms of asymptotic expansions, tried to improve the accuracy by re-expanding them in new series, and found that for quite a large class of asymptotic expansions, these re-expansions will take the same form, and he only needed two functions to represent or to express these re-expansions of remainder terms. And you will see that these functions not only play a role in re-expansions, but also when one would like to construct bounds for the remainder terms. So here are the definitions of Dingle. So the first basic terminant function, which Dingle denoted by capital lambda of order P and argument W, is defined initially by this integral representation, and it is related to the incomplete gamma function in this way. And this definition is for the order having positive real part, and the argument of W is at most pi in absolute value, strictly less. But one can use analytic continuation in W to extend the function to the whole Riemann surface C hat of the logarithm. The second function, the second basic terminant of Dingle, is defined as kind of an average of the first terminant, but it can also be expressed by this integral. And again, the order is complex, having real part greater than 0. And this time, initially, the argument of W is strictly less than pi half in absolute value. But again, one can extend this function W analytically to the whole of C hat. So the talk will consist of 3 main parts. In the first part, I will discuss a concrete example, the modified Bessel function of order 0, and how to construct sharp error bounds that are valid in large sectors of the complex plane with the Riemann surface of the logarithm. In the second part, I will talk about asymptotic expansions arising from Laplace type integrals with saddles. And the last part, the third part, will be about an implicit problem related to the large negative zeros of the ARA function. Okay. So as I said, the example will be the Bessel function, the modified Bessel function of order 0. So it was shown in 1837 by Kummer that the modified Bessel function of order 0 has this asymptotic expansion as z tends to infinity in sectors of this form. So there is a leading order behavior exponential decay on the positive axis times a divergent series in inverse powers of z. And the coefficients can be expressed explicitly in terms of factorials in this way. Now, the rays with phase 3 pi over 2 and minus 3 pi over 2 are the anti-Stokes lines for this expansion. So in the Poincaré sense, this is the maximal region of validity. And the rays with phases pi and minus pi are the Stokes lines for the asymptotic expansion. And our goal is to obtain sharp error bounds for this expansion by finding a suitable representation for the remainder term. And to do that, I will use the so-called Cauchy-Heine trick that was briefly mentioned by Adri during his talk in the spring school. So suppose that we are on the principal sheet, so the argument of z is less than pi in absolute value. Then by Cauchy's integral formula, the K-Bessel function normalized in this way can be written as a contour integral, but the contour gamma is a keyhole contour shown in this figure. So it omits 0 and the negative axis, and z is inside the contour. Now, using Kummer's expansion, it is easy to see that if the argument of s, the integration variable, is at most pi in absolute value, that the integrand behaves as s to the minus 2 for large s. And by using the properties of the k-Bessel function near the origin, it can be shown that it behaves like log s over square root of s as s tends to 0. Therefore, if we blow up the large circular arc of the contour, then along that contour, the integrand will tend to 0. And similarly, if we shrink this small circle around the origin, then the integrand will tend to 0. Sorry, the value of the integral will tend to 0. And so, after doing the deformation, we end up with integrals along the two sides of the cut from the origin along the negative axis. So our original integral can be written as the sum of two integrals along the two sides of the cut. Now we can make simple changes of integration variables to transform these integrals to integrals along the positive axis. And then we end up with this representation. Now these integrals converge, but slowly. So we combine the two into a single integral, and then we use the following connection formula for the k-Bessel function. And with that, our result simplifies to this single integral representation, valid when z is on the principal sheet. Now this integral converges very fast because by Kummer, this k function decays as fast as e to the minus t. We have an additional e to the minus t. So we have fast convergence. And one can represent this in a different way by factoring out the leading order behavior of the function coming from Kummer's expansion. And then in the large parenthesis appears kind of the exact form of the divergent asymptotic expansion. And now we would like to obtain the asymptotic expansion truncated after a finite number of terms plus an explicit remainder. For that, we will expand the denominator here. So we'll expand 1 over 1 plus t over z. This can be done as follows. You observe that for any non-negative integer n and positive t, and z in the principal sheet, this formula holds. This is just the geometric series with remainder. So this is an identity. We substitute it into this integral and then integrate term by term. And then we obtain from the Cauchy-Heine representation Kummer's expansion truncated after capital N terms plus a remainder. This time the coefficients are expressed as kind of Stieltjes moments, if you like, of the k0 Bessel function. And the remainder term has this Cauchy-Heine-type integral representation. Now one can use this representation to obtain bounds for the asymptotic expansion. And this was carried out in 1990 by Bill Boyd. In fact, he considered the k-Bessel function of order nu when nu is real and is at most 1/2 in absolute value. And this is what Boyd found. So when the argument of z is at most pi/2 in absolute value, then the remainder term in absolute value is bounded by the absolute value of the first omitted term. So that is nice. And as we leave the raised pi/2 or minus pi/2, the bound becomes increasingly worse. Note that at pi, this cosecant will blow up. So this bound is not realistic near the raised pi minus pi, which are the Stokes lines for the expansion. To overcome this problem, Boyd provided a different bound. So this is for values of the argument close to pi or minus pi. This time he could not manage to obtain a bound involving the first omitted term. So this bound is in terms of gamma functions and powers of 2. But using Stirling's formula and the explicit formula for the coefficients, one can show that this bound for large n is asymptotic to 2 times square root n times the absolute value of the first omitted term. But note that we cannot replace this upper bound by this quantity because this is always strictly smaller than this upper bound. But it would be nice to have something involving the first omitted term also near the Stokes line. And I claim that we can do that, so we can do better than this. And for that, we have to work further on the explicit formula for the remainder term. So the idea is to replace the k-Bessel function in the Cauchy-Heine representation by an integral formula. So I'm going to use this Laplace transform representation. So this is kind of a Borel transform, if you like. I think they call it the Leroy transform because it has a branch point at the origin. So we substitute this into the Cauchy-Heine representation, interchange the order of integration, and then in the inner integral we can recognize Dingle's first terminant function, and after identification we arrive at this new integral formula. So we no longer have the Cauchy-Heine kernel, but we have Dingle's terminant as the new kernel function, integrated against something which is closely related to the Leroy or Borel transform of the function. And it is important to note that this representation is valid in a larger region than this one. So using properties of Dingle's terminant function and analytic continuation, it can be shown that this formula is actually valid up to, but not including, the anti-Stokes lines of Kummer's expansion for K0. And in a similar manner, we can obtain an analogous formula for the coefficients themselves. Now, a historical remark, Dingle himself found this representation for the remainder term, actually in more general setting. He derived this for the confluent hypergeometric function. We know that K0 is a special case of that function. But he used this formula to re-expand the remainder term rather than bounding it. So how to use this new representation to give bounds for the remainder term? We just do the trivial process. So we take absolute values, move it inside, and then we encounter the absolute value of Dingle's terminant. And we would like a bound for this terminant which does not depend on the modulus of the argument. So, not that the phase of the argument equals to the phase of Z. So if we could obtain a bound which does not depend on the length, we could factor that out. And what remains according to this formula is just the absolute value of the first omitted term. Unfortunately, we have such estimates. Here they are. So this is for positive P. So if P is positive, and if chi P denotes this ratio of gamma functions, this notation is due to Frank-Wolver. Let me note that this fraction is very closely approximated by this simple square root function. Then this set of bounds hold for the first terminant function. So in this region, the upper bound is just simply 1. Then we have a cosecant, similarly to Boyd's bounds for the expansion of the Kummer function. As I said, the cosecant would blow up at the endpoint pi, but then it is taken over by this finite quantity chi p plus 1. And then in this range, ranges, we have this bound. Now the lambda function has its own Stokes lines. The Stokes lines are at pi and minus pi. So this is the reason for this quantity chi and the cosecant appearing. And note that this upper bound will blow up at the endpoint because then the cosine is 0. And that is due to the fact that the rays with phase 3 pi over 2 and minus 3 pi over 2 are the anti-Stokes lines for the lambda function. And I also mentioned here a similar upper bound for the second terminant of Dingle that I will use later on. Okay, so if you use these estimates, then we end up with the following result. So for any non-negative integer n and for z in this sector, the K0 function can be written explicitly as a truncated version of Commerce expansion after capital N terms plus a remainder, where the remainder satisfies these estimates. So it is bounded by the absolute value of the first omitted term multiplied by something that depends only on the truncation index n and on the phase of the large variable z. So here you can recognize one and cosecant. This is exactly the same as Boy's bound, but due to the estimate for the chi function, this is a better factor than the 2 square root n appearing in Boy's estimate, and we also have the first omitted term instead of that quantity involving the gamma function. And we also have something beyond the Stokes lines, up to the anti-Stokes lines, which is increasingly worse as it should be as we approach the anti-Stokes lines. Now, it is possible to obtain error bounds for this expansion using differential equation methods because the K function satisfies a simple second order linear ODE. And in fact, Olver gave bounds for this expansion. Here they are. If you look at the two sets of bounds, you can see that the bound coming from integral methods is about twice as sharp as Olver's. But as they say, picture is worth more than 1,000 words. So here it is. In this picture, I compare the two error bounds up to the Stokes lines. So the continuous black curve is the absolute value of the remainder scaled by the absolute value of the first omitted term. I choose the truncation index to be 20. The absolute value of the large object is 10. And then I vary the phase of z between 0 and pi. The dashed line is the bound coming from the integral method, and the blue lines are the bounds coming from Olver's method. So you can see that our bound is always at least twice as good as that of Olver's. But let me emphasize that there are cases when Olver's bounds are sharper than those coming from integral representation. So it is not always true that. So none of them are superior to the other in general. So let me give another example now involving the second terminant of Dingle. This is the logarithm of the gamma function, so the Stirling-de Moivre expansion. Everybody is familiar with. So let n be a positive integer. Let z be lying on the principal sheet. Then the log gamma function is expressed explicitly as a truncated asymptotic expansion involving the Bernoulli numbers plus a remainder, where this remainder satisfies the following bounds. So I'm not giving here the derivation process, but what one can find is that the remainder is bounded by the absolute value, in absolute value by the absolute value of the first omitted term times supremum over Dingle's second terminant. And then using the estimates I provided for this function, one can simplify the bounds to this one. And so again, absolute value of first omitted term multiplied by something that depends only on the truncation index and the argument of Z. And again, this is valid up to the anti-Stokes lines of the expansion. And here's a picture again. So I scaled the absolute value of the remainder by the first omitted term, truncated at 31 terms, took Z to be to have modulus 10 and varied the argument between 0 and pi half. So again, up to the Stokes line. And the continuous black curve is the scaled remainder term, and the dashed one is the bound provided by the integral method. So it's quite sharp, as you can see. Okay, let me move to the second topic, integrals with simple saddles. So those who listened to the talk by Chris Howells during the spring school can now take a nap, because I'm going to repeat what he said. So I'm going to consider integrals with simple saddles and with double infinite steepest descent path. You can do this whole machinery more generally for integrals with arbitrary order saddles, and you can have steepest contours with finite endpoints, but I believe this is the simplest case to deal with. So we have the large parameter Z. I will denote by theta the phase of Z. Ck theta denotes the double infinite path of steepest descent that passes through the saddle point Tk of the phase function Ft along the values determined by this surface. Initially, we assume that F and G are analytic, at least in a neighborhood of the path of steepest descent. And similarly to the analysis by Chris, we consider instead of this Ik, the slowly varying part Tk, which is just a normalization by the leading order asymptotic behavior. It's given by this formula. So this is normalized so that it is asymptotically constant at infinity. And then to obtain an asymptotic expansion for the slowly varying part for large Z, one can apply the classical method of steepest descent and arrive at the expansion in inverse powers of Z, valid in a suitable sectorial region of the Riemann surface of log. And the coefficients A and K in this expansion can be described by the local properties of F and G at the turning point Tk using Perron's formulas, either by an integral representation or by this form through higher order derivatives. And now the goal is to estimate the remainder term of such an asymptotic expansion. And for that, we will need an explicit formula for the remainder term, like in the case of the K Bessel function. So we truncate the expansion after n terms, capital N terms, and introduce the remainder term R and Kz. Unfortunately, we have formulas for the remainder terms. They were obtained by Sir Michael Berry and Christopher Howells in 1991. Let me mention that this year marks the 30th anniversary of the publication of this important paper. So I'm going to summarize the theory by Berry and Howells. To state the results, I will need some definitions. The first is adjacency. So a saddle point of F different from our base saddle Tk is said to be adjacent to Tk if and only if it lies on a path of steepest descent issuing from the saddle point Tk. We need the concept of the singulant capital Fkm corresponding to the saddle Tk and its adjacent saddle Tm is defined by the difference of the phase function evaluated at those two saddle points. And I also denote by sigma Km the phase of the singulant. And we will assume that for the exact remainder term that the path of steepest descent issuing from the saddle point, the base saddle tk, does not encounter any of the saddle points of f different from tk, and that theta, the phase of z, is restricted to an interval of this form. So -1 times phases of singulants, where Tm1 and Tm2 are adjacent to Tk. We also need some assumptions, so I quickly go through it. So it is assumed that Ft and Gt are analytic in a domain delta k, depending on the base saddle. This is the closure of set of all points that can be reached by path of steepest descents, which emanates from the base saddle Tk. We assume that Ft tends to infinity in this domain, and that Ft also has several other saddle points. All of them are simple, and I index it by natural numbers. There is a condition on capital N, so this product of the power of f and g should decay at infinity sufficiently fast. And it is also assumed that there are only finitely many adjacent saddles, and that the path of steepest descent through the adjacent saddles do not encounter any of the saddle points of f other than Tm itself. This condition can be relaxed in practice, so one can have infinitely many adjacent saddles, and the adjacent contours can encounter more than one saddle point. So here's a picture of the domain delta k. So it includes in its interior the base saddle Tk, and it is bounded by steepest descent contours through the adjacent saddles Tm1, Tm2, and Tm3 in this case. And so here it is, the exact remainder, the resurgence formula by Berry and Howes. So let me remind you, this was Rnkz, the nth remainder term of the asymptotics of the slowly varying part. And this is the resurgence formula by Berry and Howes. So it expresses the remainder term as a sum of Cauchy-Heine-type integrals. And this sum runs over all the saddle points of f that are adjacent to the base saddle Tk. And these Tm's are the slowly varying, the corresponding slowly varying integrals over the adjacent contours going through the adjacent saddle Tm. Yes, and the appearance of the related integrals, so the similar slowly varying integrals, is called the resurgence property. So as in the case of the k-Bessel function, this is not the most convenient representation to bound the remainder term. But in the derivation of the Berry-Howes formula, this one, in the penultimate step, there is an integral representation which is more convenient for us. And I'm going to show it to you. So for simplicity, I denote by curly Cm the steepest descent path going through the adjacent saddle Tm. Then this is the representation for the remainder. Before going further, let me make another historical remark, a little known fact, I believe, that in 1933, I think, Meyer considered the problem of bounding the remainder term of the Debye expansions for the Bessel functions. And he derived a formula which corresponds to this one for the remainder term of those expansions. So he almost arrived at the Berry-Howes representation, the special case of the Bessel functions, but he did not make the final substitution, the final step that would have led him to the Berry-Howes representation. So we interchange the order of integration, and then this is valid in this sector, as I told you before. And inside here, you can again recognize the first terminant function by Dingle. There is a small issue here that we have a -1, which we have to interpret correctly because Dingle's function is multi-valued. This can be done. And then we arrive at this proposition. So the remainder term of the steepest descent expansion can be written in this alternative form. Again, integral involving Dingle's function as a kernel. And this is how you identify the branch of the -1. So the sign will depend on the relation between the argument of Z and the phase of the singular corresponding to the adjacent saddle M. And like in the case of the K-Bessel function, this representation is valid in a larger region than this one. So it is valid up to, again, up to the anti-Stokes lines. And doing trivial, oh yes, before going to estimate this, another historical remark. In a very special case and in a non-rigorous form, this formula appears in Dingle's book on asymptotics. So in Dingle's book, there is only one term, so that can correspond to the case when there is only one adjacent saddle. Dingle did not specify the branch of -1, so he just wrote -1 in place of this complex exponential. He also did not specify the contour of integration. I believe he just wrote a loop contour here. And he also did not specify the range of validity of the formula. Okay, so estimating trivially, we obtain this result. This is the global estimate for the remainder term in the steepest descent expansion. It involves absolute value of integrands integrated over adjacent contours and multiplied by supremum taken over absolute values of Dingle terminants. And again, one can simplify these bounds by using the simple bounds for the terminant function that I presented before. I'm not going to write down those simplified bounds though. So it is worth mentioning that there is a direct relation to the absolute value of the first omitted term. So by Perron's formula, the absolute value of the first omitted term can be written in this form. And then the small loop contour around the base saddle can be expanded to the boundary of the domain delta K. The boundary consists of the adjacent contours, and then we arrive at this representation. And then now you can see that there is a close relation between this object here and the absolute value of the first omitted term. This is always at least as large because the absolute values is inside, whereas here they are outside. But it can be shown that if there are no huge cancellations inside this sum and G behaves relatively nicely near the saddle point, then this quantity is asymptotically the same as this one for large values of n. So we expect this bound to be quite sharp in general. And in fact, in many cases, one can use special properties of the concrete problem, special properties of the adjacent contours or the phase function, and do manipulations on this form before going to the estimations. And in that way, one can often obtain bounds that involve exactly the absolute value of the first omitted term. And I'm going to show you such an example without going into any of the details regarding the calculations. So this example is the parabolic cylinder function. So Nemes showed that the parabolic cylinder function with these specific arguments have an asymptotic expansion of this form. So this is when the first parameter is large and negative. The second one is large and is at least as large as 2 times the square root of the large object. That is a leading order behavior and the divergent series in inverse powers of mu. These coefficients are polynomials in hyperbolic tangent of alpha of degree 3n and can be computed by this recurrence with the initial value, the initial coefficient being 1. And one can derive this expansion with an exact remainder term by applying the Berry-Howells argument for this integral representation. So I just show you the final result. Here it is. We can complexify the large object, the mu. So the result is that for any non-negative integer n and for mu lying in this large sector, we have them as expansion truncated after capital N terms plus a remainder. And this remainder can be estimated as follows. So the analysis initially gives you the absolute value of the first omitted terms times a supremum over the terminant. But this object here is real and positive. And so by our bounds, simplified bounds, the simplified bound will not depend on alpha. We only depend on the argument of the large object mu and on the truncation index n. So this is the simplified bound. Absolute value of the first omitted term times the familiar objects here. So again, the raised pi and minus pi are the Stokes lines, and these are the anti-Stokes lines where the expansion blows up, and also the bound will blow up at the endpoint as it should. Okay, let me move to the third and final topic. So this is an interesting problem because unlike the previous ones, in some sense, it is an implicit problem. So it is well known that the ARA function AIZ has an infinite number of negative zeros, and we denote these zeros by AK arranged in ascending order of absolute value with K positive integer. And it is also known that the large negative zeros of the function, so the AKs, possess this divergent asymptotic expansion for large K. And this quantity gamma K is just a linear function of K given by this formula. And so there was a conjecture posed by Frank Olver in 1999 about this expansion, and it as follows. In the expansion of the large zeros, the nth error term is bounded by the first neglected term and has the same sign for all values of n at least 1. So the first remainder is what comes after 1. The second is what comes after these two terms, and so on. Moreover, Olver conjectures that starting from the second term, the terms alternate in sign. And this is what we can see here. So the signs are alternating plus, minus, plus, minus, plus, and so on. And Olver used computer algebra to compute explicitly the first, I believe, 90 coefficients. And he observed that this sign pattern continues to hold at least up to the 90th term. Hence made this conjecture. And to settle this conjecture, one would need to obtain an explicit formula for the remainder of this divergent series and estimate that remainder. The issue here is that this is a very implicit problem. So this time we don't have any integral representations or differential equations to start with. This expansion is coming from an inversion of an asymptotic expansion for the so-called phase function of the ARA function, which is itself a quite complicated asymptotic expansion. So this seemed to be a rather difficult problem. But using complex function theory and asymptotics and the Cauchy-Heine argument, I managed to prove this conjecture. I cannot go into the details, but the proof depends highly on this theorem that I'm presenting here. So the theorem says the following. There exists a function capital TW, which is analytic in this closed sector and has the following properties. For each positive k, T evaluated at these gammas, so these quantities, returns the k0 times -1. This function remains bounded as W tends to 0 in this sector. For any positive S, so the function evaluated along the positive imaginary axis multiplied by this complex exponential has negative imaginary part. Normalized by W to the -2/3, this function behaves asymptotically like this at infinity in this closed sector. And finally, this quantity as a function of S decays to 0 faster than any negative power of S. And using these properties, one can write down, using the Cauchy-Heine trick, an integral representation for the T function, and then expand the integral using the geometric progression, like in the K-Bessel function, to arrive at this result, which is as follows. So for every positive integer k and positive integer capital N, the k is -0, which is the same as -t at gamma k, equals the asymptotic expansion of the large zeros truncated after capital N terms plus a remainder term. These Tn's are the rational numbers, the coefficients appearing in the expansion. But this time they emerge as kind of Stieltjes moments of a function that appeared in the previous theorem. And we also have an explicit formula, again a Cauchy-Heine-type integral for the remainder term. And notice that again there is some resurgence going on because the function capital T reappears in the remainder term for its own asymptotic expansion. So the first observation is that, as the theorem says, this quantity here, when S is positive, is always negative. So this integral is negative. So the sign of this object is -1 to the n plus 1. So the sign of Tn is -1 to the n plus 1. And this shows that the coefficients are alternating in sign. And this proves the second part of Olver's conjecture. Now, what about the remainder term? Well, we notice that 1/1 plus S over gamma k squared is always between 0 and 1 for any positive S and any gamma k. So we can use the second mean value theorem for improper integrals to kind of factor out a number that depends on k and capital N only, and which is always between 0 and 1 times what remains from the integral representation. Now we just notice that this part here is the same as this one, but with little n replaced by capital N. So we recover here the first omitted term multiplied by a number which is always between 0 and 1. So we can see that the absolute value of the remainder term is less than the absolute value of the first omitted term, and it also has the same sign as that term. And this answers Olver's conjecture in the affirmative. Thank you for your attention.
Okay, thank you very much. I guess there's applause from other people as well. Thanks for this very clear talk. Are there any questions? Let's see if something happened here. Oh, so I see more applauses in the chat. But maybe let me start maybe with the question. On the previous slide, 29. So, of course, you probably can do re-expansions for this remainder as well. But even in knowing what the optimal number of terms might already be very useful information for people who actually use the asymptotic formulas. Have you computed that one?
Yes. So the original goal was to establish the conjecture by Olver, and that could be done using rather classical tools from complex function theory and asymptotics. So the truth is that this object here actually decays exponentially fast, as one would expect. But for that, I believe you have to use Eka's theory of resurgent functions. And so you can describe the precise decay rate of this object. And with that, you can obtain the asymptotics of the rate coefficients and then determine the optimal truncation. And then you can do re-expansions. If you're interested in the zeros, then you are on the positive axis. So this information is enough to obtain local hyperasymptotic expansions, which would be quite useful since gamma is positive. If you want to go for some reason close to the Stokes lines, which are in this case the positive and negative imaging axis, then you again would need a Eka's theory to describe the asymptotics precisely of this quantity here. But everything is possible. It's just a question of how much you want to work.
So there's a question in the chat from Andre Voras, and he writes, the ARA zeros are eigenvalues of the Schrödinger equation with linear potential on the positive real axis. Can you use WKB expansions to study your problem?
I guess you could use WKB to obtain the asymptotic expansion for the zeros, but probably not exact remainder terms.
Okay.
I'd just like to remark on the connection with quantum field theory. In 1982, Atouf got us interested in quantum chromodynamics, but in 2 dimensions. And in 2 dimensions, the gauge field has no dynamical degree of freedom. So essentially you're dealing with quantum mechanics. Not surprisingly, it's the ARA problem. There was a lot of interest in testing the techniques that Arkady Weinstein and Misha Schiffman had developed for 4-dimensional gauge theories on this 2-dimensional model. And that involved me in 1982 doing calculations on the Borel transform of ratios of area functions. So the subject was alive and well in a toy quantum field theory 40 years ago.
Mm-hmm.
Thank you.
Maybe since we have this over conjecture on the screen anyway, isn't there a similar conjecture for Bessel functions? So which would be more general than this?
There is one indeed. So there is a conjecture about the Mach-Mahon expansions for the linear combination of J and Y Bessel functions. So for the large positive zeros, when the order of the functions is between -1/2 and 1/2. And it stays the same, that the remainder is always bounded from above by the first omitted term in absolute value, and it has the same sign. And actually, I proved that conjecture as well using similar techniques.
Very nice. Are there any more questions, either in the chat or direct, or observations or remarks? If not, then we can maybe stop recording, and then people can just start talking directly to us and to each other.